So our goal is to figure out how to write mathematically. We're going to use our propositional variables and our propositional expressions as the building blocks for our quote-unquote essays. And that means I need to be able to use them to get conclusions out of them. So, the formal logical idea here is to make inferences. You've heard this term in statistics. We talk about descriptive statistics and inferential statistics. The goal is to draw inferences, to make valid conclusions. What we're really doing is we're building an argument. An argument is a sequence of statements that ends in a conclusion. Ideally, all of the statements before the conclusion itself are called premises. So I have premise, 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 conclusion. An argument is valid is one in which the truth of the conclusion follows from the truth of the premises that come before it. Which I hope makes sense because we're thinking of this argument as a giant if-then. If the premises are all true, then my conclusion. So really, an argument isn't based on what the sentences say. It's based on the form of this sort of logical argument. I am hoping that I will be able to get a tautology from this sort of idea. Really, let me make it even more explicit. I'm going to look at something that looks like I've got premise 1 and premise 2 and however many premises I've got, then my conclusion. If I can set up something like this, that's a tautology. The problem is that when I have a lot of premises, I end up with a really huge truth table to check a tautology, right? And that's a pain in the neck or whatever other body part you want to talk about. So it would be nice if I could summarize a bunch of these tautologies in the way their forms work and just have those rules sitting in front of me. Those are the rules of inferences. By the way, if I end up with an invalid argument, there's got to be a place in my truth table where I had a false, because it's not a tautology. We're going to call that a fallacy. And the fallacies that we are going to cover in this course are related to the way in which the argument breaks. But that means I need my summary ideas. What are the rules of inference I'm going to use? Let me give you one example. Suppose I am given the following two statements. P implies Q and P. If it snows on Friday, the Middle States math competition will get canceled. It snows Friday. What should happen?
Middle school.
This, I claim this is a tautology. If both of these are true, this should be true. This is small enough in terms of the number of letters involved. I could actually check this one the long way. So let's build the parts. We're going to work inside our parentheses. So I'm going to start with the implication P implies Q. What's the column of the truth table for that? Well, then I need P again, so I'm not going to, I could copy it down, but I really don't care to. I need P arrow Q and P. So I need the and statement. What do I get when I do this and statement? I'm taking the implication and P, so I really don't need Q at the moment. Let's and those together. What do we get? Great. Now I want to do the whole thing, so I'm going to do this arrow Q. Here it might be worthwhile to copy over Q again so I can see exactly where the arrow would go, right? First row, T arrow T, is true. What about the next three rows? Why, Gracie? But all three of these start with a false, right? And any arrow that starts with a false gives me a true. So I end up, all four of them being true. That is a tautology. So I would say that if you gave me any set of logical statements that matched this form, that would be a valid argument. If the floor is dirty, then I need to vacuum. The floor is dirty. I need to vacuum. What the content of the sentences are is irrelevant. The actual form of the sentences is what matters. We tend to write rules of inference in a slightly different version than a tautology. We tend to write them by listing the premises and then we use this funny looking symbol made of a triangle of 3 dots, and we write our conclusion. That 3 dot symbol is read as the word therefore. Which means the version of the logical argument we just wrote, if I write it in this format, gets written like this. If P arrow Q and P, therefore Q. If you think about this visually, I've got an if-then statement, and then I give you the beginning part, and out pops the end, right? It's kind of like we tuck it off the arrow and put it down here. So in a very real sense, this is referred to as the law of detachment. We've detached our Q from the arrow. There is a formal Latin name for this. And I'm 100% sure that I no longer give a crap as to why this is called modus ponens, the mode that affirms detachment. So now I can write this for just about any kind of set of sentences you want. Yes? Page 83, number 3. If it is rainy, then the pool will be closed. It is rainy. What happens to the pool? There you go. That's a valid argument. It uses exactly this form. But if it is rainy, then the pool will be closed. The pool is closed. If I then say it must be raining, is that valid? This is exactly the form of the argument we were just talking about. If it is raining, then the pool will close. It is raining, Blake said, the pool's closed. And that's valid. That's using our modus ponens. That's using detachment. That's exactly the argument I just made. And now I'm asking about this set of sentences. Is that valid? Evan? Because?
I just thought about the truth table and it's kind of saying that Q is true, but it's not something about.
Aha! If we think of these as P and Q, right? Then this top sentence is P implies Q. But the second part is Q and we're claiming P, aren't we? What I've done is I've reversed the two pieces. Wait a minute, what happens when you switch P and Q? What do we call that? A converse. We've made a converse error. This is a fallacy. It's not valid. Because we replaced our idea with a converse of the idea. The other version that this is usually referred to in logic and rhetoric classes is this is called affirming the conclusion. Because remember, our consequent, the conclusion is the Q part here in this arrow. Premise, conclusion, right? I've done this the wrong way around. And so I'm saying, oh, yes, it works because the other way around. That's not right. Here's another mistake. If it is raining, then the pool will close. It's not raining. Pool is open. Is that valid or invalid? Can I draw that conclusion from the fact it's not raining? Again, Evan, why not?
And the inverse and then regular.
Again, with the P's and the Q's, right? If I think of the first sentence as P arrow Q, and the second sentence is not P. If I go from not P to not Q, that's not the same sentence. That's the inverse of my sentence. And again, I would call this an inverse error. Because I swapped the sentence for its inverse, and those are not logically equivalent. I mean, the pool could be closed because they needed to change the chlorine in the water, or they needed to paint, or something's being done with the concrete rim around the pool. I have no idea, but the pool could be closed for some other reason. The original statement is not equivalent to its converse or its inverse. So if we do that sort of logical try and switcheroo, we effed up. But there is one it is equivalent to. The original statement is equivalent to which of the other versions? The contrapositive. What's the form for the contrapositive? No? So I switch them and I negate them. So it'd be not Q arrow, not P. Let's set up that in this idea. If that's my P arrow Q, the negation of Q should result in a conclusion that says the negation of P. If it's raining, then the pool will close. Pool's not closed. Can't be raining. This is still detachment. It's detachment using the contrapositive. So I'm going to call this valid argument. I'm going to call it contrapositive detachment. And there's my logical form. Again, there's a name here. But I have rarely used that name outside of this course. If I'm talking about detachment, I'm just going to talk about whether I'm using normal detachment or contrapositive detachment. Those are all based off an if-then, right? But there are lots of other types. Page 76, there's a table. And right at the top are the two we just looked at. Modus ponens, modus tollens. Detachment and contrapositive detachment. I'm still sticking with the if-then theme. Look at the third one. I give you if P then Q and if Q then R. So what happens when P happens? Oh, click, click, the dominoes fall over, right? From P to Q, from Q to R, so if P then R. Hey, wait a minute. A to B, B to C, I called that something in algebra classes. Like with less thans, right? A less than B, then B less than C means A is less than C. We gave that a name. You remember the name of that sort of property? Well, that was what I'm using is the inequalities, but there's a prop about the A and the B and the C, about them working together like that. I can think of it like stops on a train. Want to go from P to Q and from Q to R, and go directly from P to R, right? I have to go through Q, right? I'm going on a train. Transit. The transitive property. So, like I said, there are these formal names for these. I have never in my entire adult life used the phrase hypothetical syllogism outside of this textbook because it's stupid. That's the transitive rule. But notice here, another syllogism. P or Q, but not P. If I want P or Q to be true, and I want not P to be true, what better be true? Q better be true. There it is. And disjunctive was we called the or symbol, the disjunction symbol, right? So this is a way of combining this sort of logic step with an or. If I know P is true, then P or Q must be true because the P part's already true, right? So I can add on. And the reverse, if I have an and. P and Q. The only way and is true is if both of them are true. So if P and Q is true, then P better be true. I'm taking something off. I'm simplifying my statement. I give you a P being true. I give you a Q being true. Well, then the and better be true, right? That's the definition of and. P or Q, not P or R. There's an and between those pieces. Those are both premises. I want to and them together. P or Q and not P or R. I've got two ors. Or works when one of them works, right? But I've got a P and a not P. One of those is going to work. The other one won't. Yes? So let's suppose P is true. If P is true, then this top sentence is true. But then for this bottom sentence to be true, I need R to be true, don't I? What if P is false? Then the bottom sentence has not P in it, that's true. But the top sentence needs Q because P is false. So either Q is true or R is true. And there's my conclusion. Whoa. Now, because that's a negation with one P and a not P in it, we call that resolving. And thus, this is a resolution argument. I don't want you to memorize these forms. Put a bookmark at this page, page 72. Sorry, 76. We're going to keep going back to this over and over and over. But that means I can start looking at sets of sentences and say, is this argument valid or not? And then I can just identify what rule is going on. 3A. Alice is a math major. Therefore, Alice is either a math major or a CS major. What form that we just looked at does this match? If Alice is a math major, let's give that a letter. The disjunctive idea? The disjunctive idea starts with an or statement. And then has a not in it. Did I see a not anywhere in that setup? Alice is a math major. Therefore, that was a conclusion, right? Therefore, Alice is a math major or Alice is a CS major. That's this setup, our addition setup. We added on the extra or piece. If it snows today, the university will close. The university is not closed today. Therefore, it didn't snow. Valid or invalid? And if it's valid, what form? Colin? If it snows, the university will close. If P, then Q. The university is not closed, that's not Q. Therefore, not P, it did not snow. That's valid. It's contrapositive detachment. If I go swimming, then I will stay in the sun too long. If I stay in the sun too long, then I will sunburn. Therefore, if I go swimming, I will sunburn.
It's the last one, I forget what it's called.
The last one. The last one was our resolution. Did the sentences I say have ors in them?
Is it conjunction?
Conjunction. Thing, then and. Didn't use an and, Evan? It's our transitive property. If I go swimming, then I will stay in the sun. If I stay in the sun, aha, that's this setup here. So that's valid as well. Whew. If I am building an argument, my goal is to take the sentences I have, convert them into these sorts of symbolic ideas, and then decide, can I mix and match these forms of arguments to get the conclusion I want to know about? Page 78, example 6. Here are the premises. It is not sunny and it is colder than yesterday. We will go swimming only if it is sunny. Remember, I got to figure out how to translate that only if. If we do not go swimming, then we will take a canoe trip. If we take a canoe trip, then we will be home by sunset. With those premises, is the conclusion, we'll be home by sunset, a valid conclusion? So I have to turn all of these sentences into logical ideas. And then I need to simplify. Oh, I used a contrapositive detachment here. I used a regular detachment here. And again, and the conclusion I came to is, yes, we'll be home by sunset. By sunset. Building this idea out from the sentences I've got, can I make this conclusion or not? Is this conclusion going to follow validly from the pieces you already gave me as conditions? It is not whether it is true or false. It is, does the argument you've made stay consistent with itself? We get this a lot out of the mouths of politicians. Here are my premises, here's my assumptions, and then here's my conclusion. You're like, where the hell did that left turn come from? And in rhetoric and oratory and speech, we talk about non sequiturs. This does not follow. And that's what an invalid argument is. It's something where you say, but that doesn't follow based on the rules of logic. Questions? There are dozens more rules of inference than are used in this text. We could build out tautologies that are much more complicated than these, but those usually come from these as sub-pieces. On the other hand, there are hundreds of different fallacies. I recommend that you actually look at the Wikipedia article on fallacies, because the list is probably a mile long. We're really only going to concentrate on the ones that are related to our formal logic ideas, these two, the inverse and converse errors. Questions? My eventual goal is to make arguments in mathematics. If I were being a real jerk about this, I would tell you that every argument in mathematics should be written like what I just showed you in example 6. I'd rather hit myself in the head with a 2x4. But checking whether or not something is a tautology is just a giant truth table. So this is programmable. And if you can work in a programming language for logical statements, you can learn how to write better arguments in that format. Wednesday, February 25th, there will be a Zoom meeting at 4 o'clock hosted by the Math Association of America, where a gentleman from CMU, Dr. Pavel Kovalev, is going to talk about exactly this idea using a programming language called Lean to learn how to write mathematical arguments. I will send you all a flyer. It's an hour-long Zoom call, probably be less than that. You should come. I can do these things for quantifiers as well. If I have a statement that says, for all x, p of x is true, then I could pick one. Let's use C. It must be true. What I've done is I've taken a universal statement. All full-time students at Seton Hill are taking between 12 and 18 credits this semester. You, as a full-time student, are taking between 12 and 18 credits. A universal statement to an instance. This is an X. It applies to all of them, so it must apply to this one. I've created an instance from a universal. We call such a thing instantiation. So this is a universal instantiation. I could combine this idea with an existential quantifier. If I know there exists an X where P of X is true, then I could give the X where it works a name, right? I don't know which one it's true for. There is a student at Seton Hill taking 7 credits. I don't know who it is. Let's call them Fred. Right? So I could say the conclusion here is that I gave it a name, A. So there exists such a thing. We're going to call it A. This is an instantiation again, but it's an existential instantiation. So I can pick an instance. I can say, okay, I know this holds somewhere. This one. Or it holds for all of them. So let's use one as an example. You've done this in other classes like Calc 1. Oh, this is true for all polynomials. Here, let's look at x squared. There is some number that is a root by the intermediate value theorem. I don't know what we're going to call it. We'll call it D. And then we'll talk about D as a point. Those are exactly these two examples. I don't just get away with that. What do you want to call it? I don't care. A, C, whatever we need. We can also look at generalizations. If I know some property is true, then what's the conclusion there? I even wrote it right there, didn't I? That should be a universal statement. Whereas if I were to say, this, what would I get as a conclusion from this idea? That word has changed. Something else must be different. Here, it's true for any of them, so it's got to be true for all of them. Here, it's true for some, so it's got to be true for one. Might be true for more, but it's got to be true for at least one. So these are generalizations, universal and existential generalizations, rather than instantiations. Instead of going from many to one, I'm going from a statement about individuals to a statement about a quantifier, all, or there exists. We're generalizing rather than instantiation. Page 84 again. B, every computer science major takes discrete mathematics. Natasha is taking discrete math. Natasha is a CS major. Is this valid or invalid? Is this instantiation or generalization? Those are two separate questions. But let's start with the second one. Is this instantiation or generalization? Every computer science major takes discrete math. Natasha is taking discrete math. Did I generalize or did I instantiate? Because I picked one, Natasha. Statement about everybody. Now here's Natasha. That's an instance. Is this valid? The top sentence, oops. If you are a CS major, then you take discrete. Natasha takes discrete. Therefore, she's a CS major. Why not, Gracie? Yeah, but that's so what kind of an error am I making here? Where's my invalid behavior? If I've got an error, I need to know what kind of an error I made. Evan, my converse error. Because I said if P then Q, and then I said Q and concluded P. That's a converse error. The affirmation of the conclusion. A, all students in this class understand logic, eventually. Xavier is a student in this class. Therefore, Xavier understands logic. Instantiation or generalization? I went from everybody to Xavier. Now, valid or not? If it's valid, I need to know what form it is. Detachment. This is modus ponens. Yes, this is detachment. If you are a student in this class, then you understand logic. Xavier is a student, so if P then Q, P, Q follows. Yes. But you see how I've taken my rules of inference and now added this quantifier aspect to them. And I took my fallacies and added this quantification idea to them. So even though the if then is not written explicitly, it's written as a universal or existential statement. Everyone who eats granola every day is healthy. Linda is not healthy. Therefore, Linda does not eat granola every day. I don't know, maybe Linda eats a lot of granola, but she drinks a lot of beer too. You never know. So how do I know whether this is valid or not? And is it universal or existential? I'm sorry, instantiation or generalization. Which did I do here? I am instantiating again. Something about everybody and then something about Linda. Is this a valid statement? It is. If she eats granola, then she is healthy. She's not healthy. That's not Q. The conclusion being not P is valid. Contrapositive detachment. In general, I will not write complicated mathematical arguments at this level of granular, hyper-focused detail. It is actually very difficult in my head to drill down to all of the individual if-thens and connect them in these formal fashions. Perhaps after watching Dr. Kovalev's presentation on how to do this in a programming setting, I might think differently. But at the moment, I find this to be very difficult. So what I tend to do when I'm writing mathematical arguments is write them in a little more forgiving and informal of a way. I want you to understand how difficult it is to write mathematics in this fashion. I have a book called, I wish I was making this title up, Maths Made Difficult. Not Math Made Easy, Math Made Difficult. Math Made Difficult takes 25 pages to define the number 1 in this sort of fashion. It takes almost 70 pages to prove this way that 1 plus 1 equals 2. You gotta be kidding me. So, when I actually do write arguments in mathematics, I'm going to try and do them in English. I'm still going to try and think as precisely as possible. I'm going to make sure that I am following valid argument behavior, but I'm going to write those valid arguments a little more loosely than this. For the next several classes, that's what we will be doing. We'll be talking about methods and formal proof in mathematics. Now that means I'm going to ask you to verify and prove logically some very simple and quote unquote obvious things. But you may not have actually ever thought about why these things are true before. Now, ideally that would be Friday, but Friday's the Middle States math competition. Remember the if-then I said earlier. If it snows Friday, the Middle States math competition will be canceled, and then my schedule will go all to hell. So it is possible, I was told this morning that we are expecting somewhere between 2 and 4 inches of snow on Friday. I don't know how accurate that is, but if the middle school gets delayed, they won't be able to make it here that morning. And that means you'll have Friday off without having to worry about it. But it means that later in the next week or so, there'll be a makeup day and I might have to record something to send it to you and rearrange our schedule a little. On the other hand, if you are going to be free Friday anyway, I could use a couple volunteers to help me if this thing actually happens on Friday. If you're willing to volunteer, send me an email. I'll send you one once I know everything about Friday. Otherwise, I will see you all on Monday. Have a wonderful weekend.